Hi, good afternoon. My name is Gabriele Jost. I work in the scientific consulting group at NASA Ames Research Center. And my colleague Henry Yin, who is very active on the OpenMP committee, and myself, we experimented with the newly introduced OpenMP 4.5 Doacross support using our well-known NASPAL benchmark LU. And that's what this talk's all about. And so the outline of the presentation will be as follows. I'll give some background information on OpenMP Doacross because some people may not know what that is. I'll explain we have 6 different implementations of the LU benchmarks. I'm sure you are all thrilled to hear about it. So we look at, I will explain the different algorithms to you and focus on comparison of synchronization versus Doacross. And all the implementation work was done by my colleague Henry Yin, who can unfortunately not be here today. That's why I'm giving the presentation. I've done the performance analysis, so I will show you some performance analysis results and then summarize everything and come up with some conclusions, hopefully. So what is OpenMP Doacross? Who has heard about the OpenMP Doacross support? So, well, whether you've heard about it or not, I'm going to explain it anyhow. So since OpenMP 4, we have the ordered clause for a work share construct and an ordered construct. And with the combo of the two of them, that enables you to enclose within a work shared loop, you can enclose a structured a block of statements and make it as being ordered, and that makes it that these statements will be executed sequentially. So admittedly, that's the expressiveness of this is not very great. So you have like no possibilities to say anything about the nature of the dependence, like the distance or anything. And sometimes you may want that. So relief comes with OpenMP 4.5, which actually introduced the depend clause for the ordered construct. And the depend clause takes arguments, sync and source, which allow you to, I have a little code snippet here. So the sync argument, with the sync argument, you can specify, you can tell the runtime that here there is a point where you have to wait for a previous iteration to be finished. So in this case, it's just iteration I-1, so might directly the iteration before. And then the ordered source signals the completion of iteration I. So now everybody else who depended on iteration I can go ahead and do their work. Why would you, and this whole combo out of the Doacross construct together with the sync and with the depend clause and sync and source argument, that's what's commonly referred to as Doacross concept. So why would one want to have such an exotic thing? Well, that comes in handy for parallelizing algorithms that walk through the data in a hyperplane or pipeline fashion. An example is the overflow, the computational fluid dynamics code overflow, which employs an LU matrix decomposition with symmetric Gauss-Seidel line sweeping for an implicit portion of a time step. It's optional. And so these charts, these pictures kind of nicely demonstrate here just in 2D how you walk through the data hyperplane-wise or pipeline-wise. The LU kernel captures the nature of this code. It uses a successive over-relaxation method to solve a banded block diagonal matrix. and it's factorized into lower and upper solver steps, and both solver steps carry dependencies in each of the spatial dimensions. It's indicated here in this code snippet, and obviously there is no straightforward way to just easily put an OpenMP directive in and parallelize that. It's just not parallel. However, if you put your brains and a lot of time and effort into it, you can actually achieve a pipelined execution of the threads. So for pipelined execution, what you can do is you start all iterations of the K loop in parallel, and then all at the same time. Then you place your work share on the next innermost loop, which is the J in this case. However, before execution of the J loop, you need to make sure, you need to synchronize with your left neighbor whether the data is ready that you need it. And then after you're done with your J loop, you indicate, okay, data available. So now that looks, so you can do this. How can you do this? Now that's here being done with the routine sync left and sync right, and they're not just there, okay? You have to write them. You have to implement them yourself, and boy, that's like time consuming, non-intuitive, and as we all know, error prone. Actually, the benchmark itself had an error in it for years, but it's fixed. It's all working now. I'm not going to show the code for the sync left and the sync right, because with the people who know OpenMP, that will just trigger endless discussions. I will only tell you that it relies on testing of shared variables and employs the OMP flush semantics. That's all. That's all. I'm not going to say anything more about it. Now life has become easier. Look what with your Doacross support, you can now just no more manual implementation necessary. You use your parallel and your work share as before, except you introduce the ordered clause. You put the ordered clause on the work share, and then you put your sync here and your source here, and that's see here it's nicely summarized what I just blathered. So instead of having a routine sync left that you call, you now just specify this argument sync j minus 1, and then you signal instead of a sync right, you just say depend source. That's that. And so now nothing error prone from your side, okay? Now it's all left to the compiler. If there is an error, it's not your fault. But I mean, hopefully there is no error. So, nice and clean. I like it. Well, one might ask, where is I? Well, where do you think is I? Because we are talking about triply nested loops, it's hidden in these routines JACLD and BLTS, which somehow the mic is not really working. So, which yeah. So and BLTS is the one that carries the dependence, and so that was the pipelined version. Now, there's also the possibility to, in order to extract some parallelism, to walk through the data along a hyperplane. So in this approach, you rely on the facts that all points within a hyperplane can be calculated in parallel. So you exploit the parallelism across a hyperplane, and you don't need any further thread synchronization here, because you can do them all in parallel. However, in order to, you need to mung with the original code of the benchmark a little bit. You have to do, well, in my view, some sort of mind-bending index calculation. Index calculation, transforming the loop jk into a loop over L and jk, where L is the hyperplane, the hyperplanes, and jk are all the points within the within the hyperplane. So so you do it this way, you walk through that, and then you can do all of the hyperplane points in parallel, and then you have to do it. You do have the implicit barrier synchronization at the end of the work sharing loop. All nice, except yeah, it's difficult. It requires munging with the code. Now again, so here we employ the the Doacross support, but now we are specifying dependencies in 2 dimensions. So basically, we are extracting parallelism in 2 dimensions by this using this Doacross. And again, looks so much nicer and cleaner. Only thing, we leave the original structure of the code. We just apply the ordered clause now with the argument 2, and we have 2 depends here and 1 source. And Bob's your uncle. That's all done. Nice. So that's all you need to do. But, you know, so you leave all this work schedule and the compiler-generated synchronization and runtime library. It's all handled by them. No worry about that, which is good in one way, except on the other hand, I am not sure that really walks through the data in a hyperplane version. As a matter of fact, you have very little insights what's really going on. Okay, and that's why we you may have noticed that here we use a static work schedule with chunk size 1. Why, with the other version we didn't have to do that. Why do we need chunk size 1? Well, that led to the best load balancing. And I'll come back to that later. But you know, since we understand so little about what's going on, the way we found out is by experimentation. You know, we just saw, man, the performance is bad. You know, why? And then we experimented with the chunk size, and lucky there, look at there, it's sped up. So now if you haven't had enough of this, you can drive this a level further and now exploit the parallelism across all 3 dimensions. I don't even want to show the manual implementation of it. I mean, for me, the index calculation was already mind-bending before, but the other one, only Henry can do that. So, so anyhow. This is how exploiting parallelism in 3 dimensions would look like with the Doacross support. Again, nice and clean. All we have to do is now supply the order, now specify an order 3, and we have 3 sinks in all spatial dimension. Only little transformation with the source code that we had to do is pull the I out of these routines, which was hidden there before. And that kind of trips over any vectorization, by the way, just as a side note. So we had to pull the I out, which was not difficult. Even I could have done that, but you know, it's not so easy to optimize for the compiler. So now I show some performance results that just give some information about our evaluation environment. Basically, we are using a C on Broadwell and a KNL node. You know, just because we wanted to see if an architecture has an impact on that at all, different architectures. We also compared different compilers, the GNU and the Intel compiler, and we used an internal profiling tool licensed for NASA for profiling, and also the Parallel performance analysis tool, which is developed at the Barcelona Supercomputer Center and open source. Okay, here is the data. Here is the data for all, these are the performance for all 6 implementations. For all 6 implementations. I hope that the nomenclature is somewhat intuitive. So it's like pipe, hyperplane 2, hyperplane 3, and there is a manual and a Doacross implementation for each of them. So, and I will summarize. You can stare at the data and, you know, look at the colors, but, you know, to make it simpler for you, I will just summarize the most important findings that you can conclude from that. And the most important for us was for all three ways, for all three different algorithms, the Doacross way and the manual implementation basically have like very similar timings, which means for us you have the ease of use with the Doacross. You are not sacrificing performance. Very nice. We were so happy to see that. There's some minor insights that we gained from here. So that the hyperplane, the Doacross hyperplane, slightly better than the manual, which is not too surprising since the scheduling is somehow different. And then the architecture didn't really matter. So we observed the same behavior on Broadwell as well as on KNL. And yeah, in general, you know, we are not really into comparing these algorithms. For us, it's just important that manual or Doacross is the same. There's long papers written about why hyperplanes performs better than pipelined in most cases. I should say that these timings were obtained for the Class C benchmark, which has size 162. So good. Here's some performance data just to hammer it in even more. We used our OP-scope profiling tool, and I showed the time here for the most time-consuming thread for the pipeline version. And the tool allows me to build a vertical sum and just add up certain routines in interest. So I was interested in synchronization. So I added up the timings for the manual sync left and sync right routines, and then the partial sums indicated here. And then look at this. You know, I mean, the times in the GNU compiler runtime for Doacross, for OpenMP Doacross wait and OpenMP Doacross post, they're basically very, very similar. So nice. What's just nice to see. We also took a parallel profile, like a timeline, but you see here the horizontal axis is the time, the vertical axis is the thread ID. That's just for Class A on 8 threads. And what I want to show with this picture is we see the lower solver here, BLTS, BUTS here, and what we clearly recognize a pipeline here. Okay, so clearly recognizable. So the same thing's going on. Either way, except with Doacross, it's easier. So now, then the other thing, I've mentioned the work scheduling, and that it was like essential for Doacross hyperplane to use a chunk size of 1. Now, so I want to show some data for this here. So this shows the data on KNL, because I can use more threads there. On KNL, we compared static dynamic scheduling with chunk size 1 and just a default, which would be static with default chunk size. And as you see, the static with default chunk size, which is just chopping up the iteration space into about equal sizes for each thread, very, very poor. Very, very poor compared to everybody else. But what you see is that for 162 threads, which I can use on the KNL, you know, hyper-threading, no problem. Look how it jumps up. Now, why is that? For those of you who've seen the first slides, and remember what the size of the Class C is. 162 threads, chunk size 1, I mean, I haven't really thoroughly investigated it, but it's an interesting coincidence, isn't it? So it is my belief that for if anything that has a chunk size greater than 1 makes the GNU compiler do something really weird. You know, it completely gets out of sync, so to speak. I mean, you see enormous time spent in synchronization. As soon as it's just a little bit bigger than 1. One of them, even just one of them. So I'm not going to track down anything in the GNU compiler. However, you may ask the question, well, is this like a GNU compiler bug or deficiency or what? And so we thought, oh, we compare different compilers. We try to, honestly, we really tried. So we also used the Intel compiler, version 17 as well as version 18, and Allah, it already trips over its knickers for the pipelined execution, the Doacross pipeline, and even worse for the two-dimensional hyperplane. I mean, I don't even have, didn't even have, could let it run. It just spends enormous time in synchronization, and for the class C we then on top of everything also got the occasional race condition. So something not right, which is a pity, because for the manual implementations the performance is good. Performance is good for the Intel compiler, so it would really be nice. We've reported the bug, they're working on it, so it will be very exciting to see what it does when the bug's fixed. And but what's also kind of pleasurable to see is that the GNU compiler gets pretty much the same similar performance to Intel. Good, nice. So already summary and conclusion. So in summary, I can say, or we think that the OpenMP 4.5 adding the Doacross support was a good thing, at least in our observation. It provides ease of use of programming while not sacrificing performance. As I've mentioned before, the drawbacks is that debugging's kind of hard because debugging is hard, performance analysis is hard. So it took some trial and error and experimentation to find out that we should use chunk size 1. But I mean, that's just a matter of life. The easier it gets, the more is left to the compiler, the more is hidden from the user, the more difficult it gets to track it down by the user, because and what I find as good news is that the GNU compiler provides such good support for that and yields acceptable results. So that's that. Dum, da, da, dum, bum, bum. Thank you. You'll all deserve a T-shirt.